Question 3, we've got a white solid, MHCO3, so we don't know what this is. It looks as if it's fictitious. There's no such symbol, atomic symbol as M. There's no element such as M, so it's made up. Okay. Student has designed an experiment to determine the value of the MR of MHCO3. The student dissolved 1,464 milligrams. So we might have to convert that into grams by dividing by 1,000 at some point, I'm thinking, of MHCO3 in water, made the solution up to 250 centimetre cubed. A 25 centimetre cube sample, oh that's important, they've taken a 10th of the liquid, so 25 centimetre cubed out of the 250, they've taken a 10th of the amount. We might have to multiply up by 10 at the end. Samples of the solution were titrated with 0.102 mole per decimetre cubed of hydrochloric acid. The results are shown below. Okay, so these are volumes of hydrochloric acid. We've got 4 titrations, a rough and 3 others. Calculate the mean titer and use this to determine the amount of moles of HCl are needed to react with the 25 centimetre cubed of the MHCO3 solution. Okay, first of all, let's have a look at the titers. So it's what they start off with on the initial reading on the burette, the final reading on the burette, and they've subtracted the two to give the amount of hydrochloric acid that's been added. In the rough titer, 10 centimetres cubed, 10.00, 9.5 on the second one, 9.75 on the first one, 9.75 on the second one, and 9.65 on the third one. Now we need to decide which ones do we use and which ones to ignore. We use any two that are within 0.10 centimetre cubed of each other. So 9.50 and 9.75 are 0.25 apart. They're too far apart. 10 is way out, so we won't use the rough one. 9.50 and 9.65 are 0.15 centimetre cubed apart, so just outside the 0.1 range. So it looks as if we're not going to use the rough one at all. That's way out, and the titration 1 is over 0.10 centimetres cubed away from titrations 2 and 3. We hope that titrations 2 and 3 are within 0.10 centimetres cubed of each other, and yes they are. If you take away 9.75, take away 9.65, it's 0.10. So these two are the two to use. We call those concordant results. Concordant means the two values are within or less than, equal to or less than 0.10 centimetre cubed apart. So we're using titrations 2 and 3. So we add the two together, divide by 2, 9.70 is the mean titration. Look, I'm doing it to 3 significant figures because all of the other 3 titrations, 1, 2 and 3, are to 3 significant figures as well. Now then, calculate the mean titer and use this to determine the number of moles of HCl. Okay, so I've got the volume, I've got a concentration of HCl, I've got concentration of HCl, so concentration is moles divided by volume. My volume is 9.7. I've got to get it into decimetre cubed first of all, so volume is going to be in decimetre cubed. So 9.7 centimetres cubed up into a higher value of decimetre cubed, I divide by 1,000, 0.0097 decimetre cubed. Now concentration is 0.102 for hydrochloric acid. It tells you that in the question, equals moles divided by 0.0097. That's the volume in decimetre cubed. Multiply the two together, 0.000989 are the number of moles. And I've got it still to 3 significant figures. So now I've got the number of moles of HCl that react with the MHCO3. Calculate the amount in moles of MCH3 in the 250 centimetres cubed solution. Well, the number of moles of HCl that react with the number of moles of MHCO3, 1 mole of HCl reacts with 1 mole of MHCO3. So this number of moles, 0.000989, will also react with the same number, 0.000989 moles of MHCO3. So I've got the number of moles of MHCO3 as well, which equals this. But it's in the 25 centimetre cube sample, so I need to scale it up to what would be in the 250 original volume. So I do 250 divided by 25 is 10, and multiply by 10. I've got to multiply up by 10. So I take this value and I multiply it up by 10. So now I've got 0.00989 moles in the 250 centimeters cubed. What else do I know? Well, I know that I've got 1464 milligrams of the MHCO3 in there. I convert that into grams by dividing by 1,000. Remember, a small unit value into a bigger unit value, you divide by 1,000. I've got 1.464 grams, and now I can use moles, is mass in grams divided by MR. I don't know the MR, but I do know the moles, and I do know the mass. So the MR is 1.464 divided by 0.00989 is 147. I've got it to 3 significant figures because the other measurements are 3 significant figures as well. The student identified the use of the burette as the largest source of uncertainty in the experiment. Using the same apparatus, suggest how the procedure could be improved to reduce the percentage uncertainty in the burette. So you've got an uncertainty on a burette, and to get the error, you divide the uncertainty by the volume that's coming out of the burette. So in here, I've got 9.75, 9.65. So whatever the error is on my burette, whatever my uncertainty is on my burette, I take that uncertainty value and divide by the volume, which turns out to be 9.7 as a mean value, and multiply by 100. Now, if I'm dividing by a number, the larger this number is that I divide by, the smaller the error. So let's say, I don't know, the uncertainty on a burette was 1 centimetre cubed. It's 1 divided by 9.70 multiplied by 100. If I made that 50, it would be 1 divided by 50 multiplied by 100. I've suddenly reduced the percentage error, made it smaller by making this volume larger, so that my uncertainty divided by the volume, if the volume is larger, this uncertainty divided by this larger volume multiplied by 100% gives a smaller percentage error. In other words, I'm looking for a larger value coming out of my burette. Now, if I'm going to keep everything the same, number of moles and etc., but I want a larger volume coming out than my burette, I need the liquid, the solution, to be more dilute. So I'm going to use a more dilute solution of HCl, and that will give a bigger reading on the burette, so a larger titration reading will be needed. That will give me a lower percentage error. Okay, another student is required to make up 250 centimeters cubed of an aqueous solution that contains a known mass of MHCO3. The student is provided with a sample bottle containing this solid. Describe the method using the apparatus and the practical details that the student should use to prepare the solution. So I've got to try and get a known amount of this solid into 250 centimeters cubed in something like a volumetric flask. A volumetric flask is a flask with a mark on it, and that mark, when you fill it up to the bottom of the meniscus on that mark, it means you've got 250 centimeters cubed of solution in there. So first of all, I've got to get the solid out of the sample bottle. I've not got to get it all out of the sample bottle. I've just got to know how much has come out of the sample bottle, because it says I've got to have a known mass. So as long as I know how much I've taken from the sample bottle, that's okay. So what I'm going to do is I'm going to put a beaker onto a balance. I'm going to press the tare button. The tare button zeroes the balance, so it imagines that the beaker isn't there. And I tip the solid into the beaker, and I record the mass on the balance. I could have measured the mass of the beaker beforehand and measured the mass of the solid in the beaker and taken it away, but I think it's just easier to press the tare button on the balance, and then it ignores the mass of the beaker that you're pouring it into. Now then, I've got the solid in the beaker and I've got to get into the volumetric flask. So how am I going to get a solid into the volumetric flask? Well, first of all, I can dissolve it in a little bit of water. That'll make it easier to pour then into the volumetric flask. So I'm going to add some distilled water. Use distilled water because it's got no impurities in it. Stir it, swirl it to try and dissolve the solid. And then you can tip it into the volumetric flask and then wash out any remainder. So pour that solution then into the volumetric flask, wash it out, so wash out the beaker, pour a little bit more in, wash out the beaker, pour a little bit more in, until all of the solid has been removed from the beaker, and any little bits and things have been washed out of the beaker into the volumetric flask, and then you make it up. You pour more of the add more distilled water until it comes up to the 250 centimeter cubed mark on the volumetric flask.